Okay, now see the question. A narrow beam of protons and neutrons, each having the same momentum, enters a region of uniform magnetic field directed perpendicular to the direction of momentum. What would be the ratio of the circular paths described by them? So for this question, we need to know the exact relationship for the circular path. Okay, first we know BQV equals to M V square divided by R. This relationship you should remember. Okay, then we know V and V get cancelled. R equal to M V divided by BQ. Here they have mentioned momentum same. P equals to MV, which is equal to a constant.
Yes, sir.
Then replace this as P, BQ. So why this particular term is given? No, in this kind of cases, you don't need to worry about the velocity and the mass of the particular object, particular particles. Okay, they may be different, but their product remains same. Okay, in order to get the same momentum, the protons, actually proton, the mass is m. If it is m, the neutron mass is 2m.
Okay, sir.
Because protons, yeah, proton we know it is 1 1, but neutron we know it is 1 2. The mass is 2 times bigger. Okay,
Yes,
but
sir.
we need to go for the ratio of the circular paths. Ratio of the circular paths means R1 divided by R2. Otherwise, R proton divided by R neutron. Okay, now one more thing we should understand, and about the charge. Charge Q of each particle. For proton charges E, neutron also charges E. There is no change because neutron also having the same atomic number. There is no change in the atomic number. Neutron means 1H, proton 1H1, neutron 1H2. That's all. It is an isotope. There is no change in the charge. Therefore, the ratio Rp by Rd is here. The magnetic field is also the same because both the charges are entering into the same magnetic field perpendicular to the direction. See this particular point, direction of motion. It means that suppose this is a region of the magnetic field acting into the plane of paper.
Mm.
Okay, the magnetic field acting into the plane of paper, the particle enters in this direction. The charged particle entering into this plane, and we know the direction of velocity, direction of momentum, they are same. Okay, therefore the velocity vector v vector is perpendicular to the b vector, so it is inward. B is inward, and velocity is in this direction. So 90 degree. Okay, but now come to this point. So momentum same, charge same, magnetic field is also same. Therefore, the ratio is 1 by 1. That's all.
Oh, okay.
That's a very simple question. Because the momentum is same, also the charge is also same. Sometimes they may ask this question little bit different. I'll explain that also. So instead of neutron, suppose if they have given proton and alpha particle. In this case, okay, we'll go for the general solution. Okay, instead of going for the same momentum, we will go for the same problem in different manner. Okay, we know the symbol of proton. It is 1H1. Alpha is 1, so 2He4. Therefore, mass of the proton is m, and the alpha particle it is 4m. Charge of the proton is E. Here it is 2e. Do you understand?
Yes, sir.
So instead of going for the same momentum, we'll go for the general case. We don't know about the velocity. Therefore, R1 by R2, otherwise all R proton divided by R alpha equals to, all the cases magnetic field will be the same. So because they are entering into the same region of magnetic field, therefore B remains constant. So M, V and Q are variable. So radius is depending on mass of the particle, velocity and charge of the particle. Therefore, in this particular case, R is proportional to mv divided by q. That's all. B is constant. Therefore, here it is mass of proton, velocity of proton divided by the charge of proton, whole divided by the mass of alpha, velocity of alpha divided by the charge of alpha. Okay, just replace the values. Okay, mass of the proton is m, mass of alpha is 4m. So Vp by V alpha, you just retain it, V alpha. And you have a reciprocal. Here Qp comes to the denominator, Q alpha goes to the numerator. The charge ratio,
2E
alpha
by
to proton. So 2E divided by E. Therefore, so M cancel, E cancel. The value is 1 by 4. Vp by V alpha. Here 2 by 1. So 2 by 1. So answer is 2. Therefore, all R proton divided by R alpha equals to 1 by 2 times the velocity of proton to the velocity of alpha. So it is depending on velocity. We don't know the value of velocity. That's all. So this is the way to approach the problem. So they may change the any quantity. Okay.
Okay.
So usually they go for proton, deuteron, alpha, sometimes electron. But the problem with electron, no, the mass is very different. The mass of electron is nearly 2000 times smaller than proton. Therefore, going for this radius, no, it is extremely different. But charge is same. Charge of electron, proton same, but the mass. So mostly they avoid electron. Okay, proton, deuteron, and alpha particle they mostly choose. And one more thing, they go for same momentum, same kinetic energy. Also, they sometimes ask. So if they ask same kinetic energy, what kind of approach we should go? Instead of giving momentum or velocity, sometimes they give kinetic energy.
So
What
half
shall we
MV
say?
square.
Yeah, kinetic energy. So in this particular case, kinetic energy, it is equal to half mv square. So you just multiply and divide it by m. So you'll get mv whole square divided by 2m, which is equal to p square by 2m.
Yes,
The
sir.
kinetic energy is equal to p square by 2m. Therefore, p equal to root of 2km. Okay, the momentum relationship. So we know mv square by r equal to bqv. So vv get cancelled. So p by r equal to bq. Therefore, r equal to p divided by bq. So instead of p, you just replace
Root K.
2km divided by bq. Okay.
Yes, sir.
And one more thing, you might have studied in dual nature lesson. Particles accelerated by potential. Particles accelerated by potential. In that particular time, the kinetic energy of the particle is equal to QV. QV, potential capital V, not small v, capital V, voltage. So accelerating potential. So we studied the same concept in dual nature. Sometimes they link the concepts. The same question will be asked in different kinds. Even they go for what is the ratio of the de Broglie wavelength. Otherwise, they go for the radius of the track, circular track.
Okay, sir.
The concept is same. Concept is same. If it is a circular path, obviously we have to go for this particular equation. Okay, but in case of de Broglie wavelength, you don't need to worry about the circular path. De Broglie wavelength is something different, but the concepts are same. So kinetic energy must be converted into p square by 2m. So k equal to p square by 2m. You just memorize this formula. Okay, p square by 2m. Otherwise, you just have a multiplication of m and u. Okay, you will get the answer. Also, kinetic energy of the charged particle is equal to qv. So this one also we know qv. Work done is equal to, we know work done equal to change in kinetic energy. That's all. That is why we are using this particular equation.
Okay, sir.
And now see this question. You try to solve this one. Question number 10. Okay, you better try to solve this one. Particle A and B masses. For this kind of cases, no, you just have a column. Okay, mass m and 2m, charge q and 2q, and both these particles moving with the velocity v1 and v2. Same direction, enter the same magnetic field. So B is same. So no need to worry about the magnetic field. Enter their motion. The forces FA and FB, FA and FB, and the ratio is FA by FB equal to 1 by 2. Find the ratio of their velocities. We need to find the velocity ratio. That is the question. You understand the question?
Yes, sir.
Okay. Use this particular data, and we know R equal to mv divided by bq, right? Mv divided by bq. And this question, radius is not given.
Yes, sir.
Radius is not given, and velocity it is given as v1 and v2, and force bq. Okay, force is the ratio of okay, suppose if we write this one, FA equal to BQ V1, FB equal to B2Q V2, right?
Yes,
Now
sir.
divide these two quantities. Divide these two quantities. So we know there no need to go for this particular one. Okay, no need this one. So you just have this direct formula itself. And ratio FA divided by FB equals to, we know BQ V1, B2Q V2. So QB all get cancelled. FA divided by FB 1 by 2. Here also 1 by 2 V1 by V2. So the ratio get cancelled. 1 by
So
1.
V1 is equal to V2.
Yeah, this 1 by 1. Find the ratio of their velocities are V1 equal to V2, no problem. So for this question, we don't need to worry about the circular track. Okay, if we go for the circular radius of the, because the information about the radius is missing here. Okay.
Yes, sir.
Okay, next question. This one. For this question, question number 11, they are asking the direction of the magnetic field. The beam of alpha particle projected along x-axis experience force due to the magnetic field along the y-axis. What is the direction of magnetic field? Okay. For this case, no, already we know the formula. F equals to Q V cross B. Q V cross B. Okay, I'll tell you one small trick in this case. Okay, suppose if they ask any MCQ question, no, we know the pattern. They are asking the direction of magnetic field only, not the force, because already they have given the direction of other two quantities. Okay,
Yes, sir.
you just have a normal condition. Okay, the direction of velocity. The particle is projected along the positive x-axis. Therefore, v it is in the I direction. Okay, here the answer
Yes.
is the magnetic field. It is along the positive y-axis, j cap. So what must be the direction of b so that it is j plus j? We know I
K, sir.
to j,
K.
yeah, I to j and j to k.
K.
I cross j. I.
Cross K is J.
Wait. I k. No, it is not I cross k. K cross I. K cross I. Therefore, it must be negative k.
Ah.
Negative. If you multiply with the negative k, you will get exactly the j value. So this is the simple method to solve this question. Okay, and now we'll go for the direction in the textbook. Okay, how they have used the actual concept. Otherwise, we have to go for the rule. Okay, Fleming's rule, Fleming left-hand rule. Okay, actually, this process is something like we are getting the answer from the backside. Okay, it is a reverse process, but we cannot write this answer in the examination. No, in case of
Yes,
descriptive
sir.
type question, it is no, it is not. They don't evaluate. Okay, actually, they don't give a mark. But actually, the answer is correct. It works with the MCQ questions. Okay, but here we have to go for the rule. The rule is Fleming left
Left
hand
hand.
rule. Left hand rule. Okay, Fleming left hand rule. We know the middle finger, thumb, and forefinger. Okay, middle finger, thumb, the forefinger. Middle finger direction is magnetic field, right? Magnetic
Yes, sir.
field. Thumb represent the force, and forefinger. Sorry, middle finger is direction of velocity. Forefinger is the direction of magnetic field. Okay, and they have given XY axis. So X axis and Y axis. X axis direction of velocity and Y axis direction of magnetic field. Okay, and sorry. Y axis is the force, not magnetic field. It is force. Y axis it is force. Therefore, the other one must be in the negative. Sorry, not negative. It is in the Z direction. It must be in the Z axis. Okay, the quantity magnetic field must be in the uh, Z axis. Okay, in what direction, positive or negative? That we must understand. Okay, we need to go for the cross product rule. Okay, suppose we know the cross product if the particular quantities. Okay, v it is in one direction and v in xy plane. Sorry, not xy plane, xz plane, and b it is also xz plane. X v cross b. If it is v cross b, no, v cross b, the direction of force in the perpendicular direction. Okay, this is the way to get the direction of magnetic field. Oh, sorry, force. Direction of the magnetic force. It is like it must be in the xz plane. Xz plane. Suppose if I take this as x axis and this as z axis, z axis, the force must be perpendicular to both the xy axis. But here we usually take the outward direction as positive z axis. Okay, not this direction. This one is negative z and this one is positive z. Therefore, in this particular direction, we will be getting the negative z axis. Negative z axis. Here, our magnetic field is pointing in this direction and velocity it is pointing in this direction. Here we have 90 degree. So perpendicular to V and B, we are getting the force value. So it is based on Fleming left-hand rule. Otherwise, the vector right hand curl rule. Right hand curl rule. It is in the direction. It is in the direction of z-axis. Okay, next. What is the direction of force acting on the particle velocity in uniform magnetic? That it is a direct question. Question number 13, it is also similar to the same. An electron is moving along positive x-axis. In the presence of magnetic field along the positive y-axis, what is the direction of the force? So it is perpendicular to xy plane. So it is in the z direction only. But z direction, whether it is positive or negative, we have to find.
So it is
because electron, it is negative. No, suppose if you apply the Fleming rule or right hand thumb rule. Okay, we'll take this question. Here they have asked the direction of force, so it is easy only. In the previous case, they have asked the direction of magnetic field, so we cannot directly write the answer. But this case, no, the direction of electron, the motion of the electron. But there is a small change. So the rule is only applicable for the positive charge. If the positive charge is entering in this particular direction, no, we will get one answer. But the charge is negative. Here it is negative charge. So we will come the direction of velocity and in x-axis and the direction of magnetic field in y-axis. So therefore, z direction, in z direction, the force will be there. Okay, now to check, it is a negative charge, negatively charged particle. It is entering in this particular region in the velocity, with the velocity v. See, actually, the Fleming rule, no, Fleming left-hand rule, if we stretch over all the fingers, the middle finger represents the direction of the positive charge.
Yes, sir.
Okay, middle finger, direction of the positive charge, and the forefinger represents the direction of thumb, direction of the magnetic field. Then the thumb, actually, it is pointing, it is out of the plane of paper. Actually, if we keep our eye in the direction of the paper, no, or in the xy plane, the thumb, the extended thumb, it is perpendicular to the xy plane. Therefore, in case of positive charge, the force is in the positive x-axis. But here the charge is negative. Therefore, the direction must be in the negative z-axis, not in the positive z-axis. It is in negative z-axis. Do you understand? Actually, in case of Fleming left-hand rule or right-hand palm rule, we always have a reference of positive charge. The direction is applicable only for the positive charge. In case of negative charges in motion, the direction of thumb, no, it represents only the direction of the force of positive charge. Okay, similarly, in case of right hand palm rule, if you take right hand palm rule, the in the direction of the palm represents the direction of motion, force. Suppose in this particular case, the magnetic field in the y-axis, the thumb represents the direction of the positive charge. The palm will give you the direction of the force. Here also the palm, it is facing our face. Okay, therefore it is the direction of the positive charge. Okay, in case of negative charge, it is the back side of the palm. Okay, that is why in this particular question, the direction is along the negative z-axis. The direction of force, it is in the negative z-axis, not in the positive z. Okay, you have to visualize the concept. So the rule is only applicable for positive charge. If it is negative charge, you have to go for the opposite direction. Any doubt?
No, sir.
Okay, this one question. Question 18b. Here they used to ask this kind of question also. We have to draw the trajectory. Say a neutron, electron, and alpha particle moving with equal velocities enter a uniform magnetic field into the plane of the paper. Trace their paths in the field and justify your answer. See, for this question, no. Again, we have to go for the equation because electron and alpha particle, neutron, we know it is neutral, it is not deflected. Okay, neutron will go in the in the same direction. Okay,
Yes,
it will not get any deviation. Neutron will go in the same direction. But the radius as well as the direction of the particles, we have to understand. See, alpha particle, it is positive charge. Electron is negative charge. Already, as I told you, know, here you go for the, again, right hand palm rule. The magnetic field, it is into the plane of paper. Okay, the four fingers. Okay, suppose if we use the right hand palm rule, the four fingers, it is into the plane of paper, and the thumb represents the direction of positive charge. Therefore, the palm represents the direction of force. Therefore, alpha particle, it is deflected in the upward direction, and
yes,
electron is deflected in the downward direction. But one more thing, the radius of the size of the radius, because we know they are moving with the same velocity. They have told moving with the same velocity. Therefore, R is equal to mv divided by bq. mv divided by bq, and the charge and mass. Therefore, R is proportional to mass of the particle and charge of the particle. Okay. For this particular case, mass of electron and mass of alpha particle, they are extremely, they have a bigger difference. Already I told you, alpha particle is helium nucleus 2 4, but electron, we know it is a very light particle. Electron is a light particle. The mass is actually 2000 times smaller than proton. Okay, in case of helium, no, it is extremely smaller. And charge for both the cases, electron as well as helium, only 2 times different. So it is E, it is only 2E. So there is no much difference, but the mass, it has bigger difference. Okay, therefore the dominant factor is mass only. Therefore, alpha particle will have a longer trajectory. Okay, the trajectory is very long. The circular path is very having bigger radius, and electron is having a smaller radius. That's all.
yes, sir.
Here we have to mention that also. The radius of alpha particle is greater than the radius of the electron, because R is here proportional to M. Okay, proportional to M, charge M by Q also, but charge mass to charge, that ratio is very bigger for alpha, not electron.
So the electron's mass is
It is very small. I told you, no, mass of actually mass of proton, no, it is 1876 times the mass of electron.
okay, okay.
So that is why we can directly go for 2000 times, nearly 2000 times the mass of electron. Mass of helium alpha is 4 times mass of proton. So 8000 times, nearly 8000 times it is greater.
Okay.
8000, so divided by 2, 4000 times. The radius is 4000 times greater. It is extremely greater in size.
Okay.
Okay, similarly, in this case also, alpha and proton. Here, both the particle experience the upward direction, the force in the upward direction. Only the difference is the sizes are different. Okay, the charges for alpha, the charge it is 2 times electronic charge. Proton is 1 time the electronic charge, and mass proton is m, alpha is 2m. So calculate the size of the radius and draw the trajectory for this case. Question number 17. Okay, it is similar, the same similar question only. And they also ask you to find the ratio of the radii of the circular paths which the two particles may describe. So the question number 17, it is easy now.
Yes, sir.
Sorry. Okay. Question number 21. All proton and neutron having equal momentum enter into a region of uniform magnetic field. Sorry. So this question only you have to draw the diagram, trajectory, the diagram it is needed. That's all. So mostly all the questions will be having the same pattern. Okay, only question number 20. You see the question. An electron
Yes.
is moving horizontally with the velocity 4 into 10 power 4. Enters the region of magnetic field 10 power minus 5. Acting vertically upwards in the figure. Draw the trajectory. And find out the time it takes to come out of the region of the magnetic field. Who shall we find? This one. Wait a minute. So drawing the trajectory, it is okay. We have to find the time it takes to come out of the region of the magnetic field. Okay, wait a minute. I'll see the solution. 20. Actually, it is having semicircle. So it's having it is a semicircular track. Okay, see this one. We know BQV. It is the force experienced. The time period formula we already studied. Okay, which is R equal to mv divided by BQ. Time period is equal to 2 pi R divided by V, right? 2 pi R divided by V. So 2 pi R by V, it is equal to M by BQ. M by BQ. Okay. Okay, now we just draw the diagram. Actually, they are asking. So it enters the region. What happens now if they have it is entering in this particular direction, the electron. As per the rule, electron enters into this region. So the magnetic field into the plane of paper, it is moving in the down upward direction. Sorry, in the downward. Wait a minute. We'll draw like this. The electron will get the force which is in the downward direction. So whenever the electron enters into the region, no, it experiences force in the downward direction. So it get deflected in this direction. Okay, and then it makes circular path. What happens? No, it completes only semicircular path. And then it comes out of the field. See, most of the charged particle, if the magnetic field it is it is having very bigger area, no, the coverage area. If it is very bigger, sometimes it may complete full circular path if it is released in the center.
Oh,
Okay. Otherwise, they come out of the region. They may come out of the region, but for this particular kind of case, no, it may go into the region and then come back. Okay, come back by completing a semicircular track. Okay, but for this case, no, you will get only T by 2. Not exactly T, you will get only T by 2, the actual time.
okay.
Okay, now the T by 2 is T equal to pi m divided by BQ. Pi m divided by BQ. We know pi equals to 3.14. M mass of electron, we know 9 times 10 power minus 31. Okay, and magnetic field it is 10 power 5 minus 5. And charge of the electron is 1.6 10 power minus 19. So it is about 1.766 microsecond. Okay, it is around 1.766 10 power minus 7 minus 6. Is a calculator. Second, I have converted this 10 power minus 6 into microsecond. Okay. We'll check the answer, textbook answer. Question number 20, right? So 1.77 microsecond. So correct only.
Yes.
Actually, they have made a mistake in this diagram. Actually, the negative charge will not experience the upward direction force. It is in the downward direction. They made a mistake in this case.